that will come up. Okay, so that is all the four mechanisms, SN2, SN1, E2, E1. Now let's put them all together. I gave you guys a handout, which is kind of a worksheet, but I also gave you guys this handout, right, which compares all four of them, four of the mechanisms. Do you guys have that handout? Okay. Now, use it enough that you don't have to keep it in front of you, because it's not something you can use during exams and quizzes. Does everybody have a copy of that handout? It's on Canvas as well. Now, do you guys see at the bottom of the page where it says good nucleophile, weak base?
Yes.
I missed one. Could you add that? Okay. Do you see at the bottom of the page where it says good nucleophile and weak base?
Yes.
Another one that you're likely to see enough, actually decently enough times, plus weak base. Can you add azide ion? N subscript 3 minus 1. It's an azide ion, which is not a good base at all, but a very good nucleophile. So, yeah. Okay, so how do we decide whether a certain reaction would go predominantly through SN2 or SN1 or E2? E1 is never major. E1 is never the major pathway. It's there, it's fine, it can give a minor product, but E1 will never give us the major product, period. So it's really a comparison between SN2, SN1, E2. That's really the three comparison points. So first we look at the substrate. Go ahead, take a look at the first example, please. Keep this in front of you. The first example on the worksheet, does everybody have a copy of that?
Yep.
CH3OH.
This one? Okay.
The first example of the worksheet that I just gave you guys today.
Bromide. 2-methyl,
So-
2-bromo, 2-methyl
Okay.
butane.
So first thing we do is we look at the substrate, guys. Is that a primary substrate, secondary substrate, or tertiary substrate?
Tertiary substrate.
So tertiary substrates can only do two things. Can they do SN2?
No,
Can
they
they
can't.
do SN2?
No.
No.
How about SN1?
Yes.
How about E2? Yes, they can.
E2?
E2 they can, SN2 they can't, because E2 means one of those protons are being taken out, which is fine because it's not at the tertiary center, it's on the beta carbon. So yes, E2 they can. Everybody good? Now, what will decide whether the tertiary substrate goes through SN1 or E2?
CH3O Na.
Who is going to decide that?
Oh,
What will SN1 need?
AOH.
Sorry, actually no. It's a weak nucleophile and a weak base.
Weak nucleophile and weak base.
Will
So
exactly,
water,
water,
alcohol,
ammonia.
or ammonia.
Those will give us SN1 as the major pathway, major guys. But for E2, what will we need if we wanted that to be major? We will need a strong base, exactly. Exactly. So if you look at this example, two arrows. First arrow is using methanol, the second arrow is using methoxide. Isn't that right? So what do you expect the main pathway, the major pathway to be for the first arrow? Sorry? SN1. Do you all agree? So if it's SN1, what will be the major product? Say that again? Yeah, so what will be the product? You're right. This will be SN1, absolutely right. So what will be the product?
Substitution BR
With?
Methoxide.
Do you all agree?
Yes.
Please make sure you can write a mechanism step by step because it's SN1. But what about the second arrow? Do you expect it to be SN1 or E2? SN2 is not possible. So which one do you think will predominate when you have this guy?
E2.
E2. So E2, now you're thinking, so what product would we get? How many products, E2 products are possible in this example? Anybody?
One
So what are those two? Do you agree? That
double bond.
and everybody agrees? So then our thought is, okay, two
Yeah.
possible. Is this a bulky base or a non-bulky base?
A small base.
So which will be major, Hoffman or Zaitsev?
Zaitsevs.
Would you mind taking?
Does that make sense?
Would you mind taking your?
Everybody following that?
Thank you.
So you start with the substrate, then decide what are the options. Okay, let's look at the next one. The substrate, is that primary, secondary, tertiary?
Primary.
So again, three options, SN2, SN1, E2. Which one it cannot do?
And SN1.
SN1 is not possible,
Oh, yes.
right? Primaries cannot do SN1 unless there was resonance stabilization of the carbocation. Primary cannot do SN1. So, okay, cool. What is this here? Okay. Do we all agree that SN1 is out of the question here?
Yes.
Yep.
Okay, so now once again, two choices, sodium hydroxide or, what is it? Oh, potassium tertiary butoxide. With heat, of course. Heat, yes, heat means I am kind of hinting you towards elimination, absolutely. Okay, so SN1 is out of the question. What about SN2? Is that possible?
Yep.
Is E2 possible?
Yeah. Yes.
What will be needed for SN2 now? What will
Good
be
nucleophile.
needed?
Good nucleophile weak base.
A good nucleophile will help us do this. Agreed? And what will help us do E2? Not a good nucleophile, but a good base. And hopefully a good base that is also a weak nucleophile, hopefully. Isn't that right? So what do you think sodium hydroxide is? Is that a good nucleophile or a poor nucleophile?
Good nucleophile.
It's also a good nucleophile, right? It can also be a good base though. Sodium hydroxide can do both. Hydroxide ions and alkoxide ions can do both. Be a good nucleophile and be a good base. Isn't that right? Do I say that there? Do I say that for these? These are good nucleophiles, not God.
Yes.
And good bases.
Yes.
So how do I know in the first case it is SN2 and not E2?
Did you have a good base?
Say that again.
You have a good base?
So would I get both? Should I get substitution product, SN2, or the elimination product as the major product? So what does the table say for primary substrates, guys? When it's a primary substrate and you have a good nucleophile and a small base,
You do SN2.
that's your major product. Will there be some E2? Absolutely. You can't stop it. But SN2 will be major. What if, though, I did this? I say as sodium hydroxide, but then I add heat to it. Then what?
It would go under E2.
So we still have two products, the same two products, but one, two, three, four. But then this one is expected to be major. Because temperature, high temperatures kind of push the pendulum more in the direction of elimination. Are you all with me so far? But then what about this guy, potassium T-butoxide? Is that a good nucleophile?
No, not a
It's
good
not a good
nucleophile.
nucleophile because it's so bulky. Because it's so bulky, it can't do substitution as well. So if it cannot do SN2, what will it do then?
E2.
E2. So what will be the major product? Agreed? Is everybody following the thought process here? So you got to evaluate, okay, what do we have? Is the substrate primary, secondary, tertiary? And then, okay, do we have a good nucleophile or a good base and things like that? And then come up with the conclusion. Make sense, everybody? Now, tertiary and primary are kind of extremes. The funnest ones are secondary, right? The secondaries can do the unimolecular as well as bimolecular reactions. So you got to be a little bit more careful in secondary. But let's take a look at the next one. We have this as the substrate. Are you guys with me so far?
Yep.
Now that's a secondary substrate. What does the table say for secondary substrates? So we are doing 4 things here. We are reacting this with sodium methoxide. We are reacting this with methanol. We are reacting this with sodium methoxide, but with
Heat.
heat, and then reacting this with T-butoxide with heat. Okay. So secondaries can go in either direction because they are in the middle. So now the choice is between the nucleophile / base to decide what's going to be major or minor. You good, everybody? Let's start with this guy. Is it a good base, a good nucleophile, or both?
A good nucleophile but a weak base.
That
RO.
is not a weak base. Is
Oh,
that
it's a
listed in a weak base?
No.
It's a good base and a good nucleophile.
Oh, it's a good nucleophile and a
Isn't
good
that right?
base. Okay. RO.
So if it's a good nucleophile and a good base, can it do SN2?
Yes.
Can it do E2?
Yes.
Absolutely. Now, let's take it, what's the difference between this arrow and that arrow?
The one has heat, so it's.
That one has a heat symbol on it.
Okay, Viola, can you finish what you were saying? This one what?
Well, both of them are the same. Since there's heat present on the right side, it's going to be E2 more
Good.
than SN2.
That's the comparison. Do you all, did we get that?
Yeah.
Right,
Yep.
so major, again, major pathway. I think this will be SN2, this will be E2. You guys agree?
Yes.
Okay, SN2 now, please. You got to take care of stereochemistry because stereochemistry is shown. So what will be the product? Anybody?
The methoxide is on a wedge.
So the nucleophile comes from the face opposite to the leaving group, gives us inversion at the stereo center. We good? How about there? What will be the major product? So E2. How many beta carbons does this molecule have?
Two beta carbons.
1, 2, right?
Yeah.
Yep.
So, can there be E2 on this position?
Yep.
Slow down.
Or no.
No.
What?
Can
No.
there be E2 on, why not?
Because there's stereochemistry and double bonds cannot do that.
Why not?
Because they're not antiparallel.
They can,
Oh.
but why not in this case?
Because they're not antiparallel.
Because the hydrogen is not anti.
It's
The
it's
hydrogen is syn.
it's on the same side as the
E2
BR.
requires the 2 to be anti.
Mhm.
Otherwise E2 cannot happen. You guys with me?
Yeah.
Are you recognizing that?
Mm-hmm.
So can E2 happen there?
No.
No.
Can E2 happen here?
Yes.
Yes.
Because
Yes.
there is at least one hydrogen that is on a wedge, isn't that right?
Yeah.
Opposite stereochemistry. So how many products? Just one, major, right? And what would that major product be? Do you agree?
Yes.
Is this possible? Is that product possible in this example?
No.
Possible. Are you all following? And you're seeing it come together. Okay, good. Now let's look at this guy. So, what? SN2, SN1, E2. Is that a strong base?
SN1
SN1, why SN1, Mark?
because it's CH3OH is
Because it's a weak base and a weak nucleophile. It's a
ROH.
weak base, right? So it cannot do E2 because it's a weak base. We cannot do SN2 because it's also a weak nucleophile, so it does SN1. What's the mechanism SN1? Let's run it through our minds. It goes to carbocation. Isn't that right?
Yep.
Where would the carbocation be?
Where
On this carbon?
where the
Can
BR?
it rearrange
Yes.
to create a where? Which side?
To the first
Hydride shift. Isn't that right?
Yep.
So the carbocation would be there?
Yeah.
So where would, what would be the product?
Two products.
With the bromide on the methyl.
Bromide is gone.
Oh, bromide is gone.
OCH.
Methoxide on
Is
the
there a
bromide.
stereo center? Does this have a stereo center? No, so we
No.
don't have to worry about racemic and all.
Oh.
If there were a stereo center, we would have to make sure you write that as a racemic. Because carbocations make us lose all stereochemistry control. So you'll get both products. You guys remember that? Everybody okay?
Yeah.
What about that one? Which mechanism would that go through?
Good.
E1.
But is that a weak, what is it, a strong base or a weak base? Strong nucleophile, weak
Good
nucleophile?
bulky base.
It's a good bulky base.
Oh,
It goes under E2.
So not E1 is never the point of consideration. Please never focus on E1 because E1 is always kind of sort of there.
Yeah.
But our choice is between SN1, SN2, E2. So what will this primarily do?
E2.
E2.
Now once again, what would be the major product? Can we have E2 over there?
No.
Because those are on the same side, right? Can we have elimination here?
Yes.
Absolutely. So what's the major product? So please make sure you're practicing writing these mechanisms, the steps and all, so that it sticks and you get it. Okay, that's how it's happening. Does that make sense, everybody? Yes?
Yeah.
So you kind of have to go step by step by step. So go ahead. Why don't you guys take 5 minutes, not more, 5 minutes. Let's do the remaining 2. Talk to each other, process it with each other, and let's come up with the answers for the back page. First is the substrate. That's the first thing we look at. Then we look at the nucleophile slash base, depending on what's being used. E1 is never the major pathway, so focus more on SN1, SN2, and E2.
Good nucleophile. Good base. SN2. Weak base.
Okay.
How did I do that? Something is not right here.
Oh, is it? Oh my god,
Could I ask you guys to change this structure to that, please?
And what?
The last one, the last one.
So we
Yes.
put a double. So we put
Yeah,
a.
just put a double bond there. Everything else is the same, because because I'm wondering why I had that.
Wait, which one?
The last one.
The last one.
Oh, okay. What am I missing? Oh, the double bond.
Wait, I forgot what you want.
SCH free.
Oh, because it's bulky. Oh, okay. Okay, that's what it was. I was
Weak nucleophile, weak base. Weak nucleophile, weak base. SN1. SN1.
We'll do that later. We'll do that later. We'll do it together. Let's just focus on these two. Yeah, please, please, yeah. Please.
No. Can't be that. NH2. And stereochem. Stereo centers. 1, 2, 3. There's a stereo center, so it becomes racemic. NaOET. Good nucleophile, good base. SN2.
So you are saying which mechanism, so specify which mechanism are you?
E2.
E2? Okay, cool. Do you all agree? Yeah. Because it's a big bulky base. Okay, good. Guys, can we go through this? Because we do need to finish and stuff. Oh, no, please do. Please. And yeah, please, go ahead. Let's do this faster. We do need to finish and hopefully start chapter 7. Please. Go.
SN2 center methyl shares possible. No rearrangement possible.
Are you proposing
Weak
SN2 or
nucleophile,
SN1?
weak
Yeah.
nucleophile, weak base, SN1.
Which mechanism? SN2, SN1?
This is SN1. Look at this. Yes, this is fine. There you are. Yeah, look at that.
Stereo center. And it doesn't have that.
You all agree? Do you agree this is secondary, right?
Yep.
That's a good nucleophile but a weak base. So SN2, right?
Yep.
So therefore that's the product. Please notice the inversion of stereochemistry. Viola and others, because I know a lot of you do this. So I need you guys to be a bit more careful. Where is the bond going? Is it going to sulfur or carbon?
Sulfur.
So let's make it very clear. So that's the sulfur. So there's no ambiguity. It's right there that okay. The
Good
bond is
bulky
going to
base.
make it very clear,
E2.
but you're absolutely right. Is everybody okay with that? Okay, now what about here? Do we have a good nucleophile and a good base? Yes, no, maybe? Love that enthusiasm in this room right now. But with heat.
It's good. It's a good.
So, E2?
Yeah.
So, and is that bulky or small?
Small.
So ZSEFs?
Yes.
Everybody okay?
Yep.
Cool. What about that? Good base? Good nucleophile, weak base, weak nucleophile, what? Weak, right?
Weak nucleophile,
So
weak base.
can it do E2? Can it do E2?
No.
Can it do SN2?
No.
What, and E1 we never think about. So the option is SN1. I'm glad you did that, which means racemic. Although is that the major product? Those are not the major products. So you got to process this in your minds. If it's SN1, does it have an intermediate?
Yes.
What's the intermediate in SN1?
Carbocation.
Where is the carbocation
No,
going to
it-
be?
OET.
There, right?
Yep.
Can it rearrange to a more stable position?
Yeah.
Yes, where would that be?
More near the phenyl group.
So those will be the major product. Do you see that?
SN1 plus.
So please do practice writing all the steps so that it just becomes ingrained in your minds. So the major products won't be these, the major products will be these. Do you all agree?
Yes.
Yep.
Yes? And racemic because it's carbocation. Now that one is a big bulky base, strong base with heat, Hoffman's product with E2. Everybody okay?
Yep.
Questions? Okay, let's do this very quickly, guys. Or do you want to do this at home?
I did it. I did it
Did
already.
Okay, tell me which mechanism. Once again, we have a tertiary substrate this time. That's a tertiary substrate. Okay, so what mechanism?
E2.
E2. So and it's bulky, right?
Yep.
So Zaitsev's or Hoffman's?
Zaitsev's.
So what's the major product?
Or, wait, no,
Oh, sorry,
Hoffman's.
Hoffman's, sorry. What's the major product? Anybody?
Double one will be on the methyl.
Double bond will be on that exocyclic methyl, the methyl on outside the ring, because that is the least hindered hydrogens. Everybody agrees?
Yep.
Say again?
That looks ugly.
It looks ugly
Double
because
one
my drawing is.
outside.
Yeah.
No, just the double one outside, it just doesn't look
Okay, let's see.
Yep. There we
It still
go.
looks ugly. Got it.
They don't get your
Okay.
art.
Yeah, yeah. They say chemists are good artists, but I'm an exception. I draw very well. Okay, let's talk about this, guys. What about ammonia? Strong base, weak base. Strong nucleophile, weak nucleophile. What? Weak base and
nucleophile, weak base.
nucleophile, isn't that right?
It goes under SN1.
And that's tertiary, so SN1, everybody agrees?
Yes.
Yep.
If it goes through SN1, so you got to picture this in your minds, guys. The mechanism, carbocation will form here. Can it rearrange
Yeah.
to a
Rearrangement
more
is
stable carbocation? Once you get your carbocation here, which is tertiary, right?
a methyl shift can take.
But can it make a more stable carbocation?
A methyl shift
Why?
can happen.
Why is that more stable?
Because it's allylic.
Also allylic.
Oh.
It's also allylic. That's why I changed that structure, because I was like, what am I really getting at here?
Oh.
I forgot. So, right?
Yep.
So what will the major product, how many products would you get?
NH2 in the secondary position.
But how many secondary? Why
So-
secondary?
Substituted.
Tertiary.
Oh, tertiary. Okay.
But how many? Can that be a stereo center?
Yeah. Yes.
Absolutely. So
So
you will get a racemic mixture. You'll get both in enantiomers. Agreed?
yep.
Everybody? Again, please write the mechanisms over and over again. Next one, it's tertiary substrate with a good base, good nucleophile. Can it do SN2 if it's tertiary?
No.
So what's the other option?
SN1.
SN2. That's a good new base.
Wait,
and a
E2?
good E2. Exactly. Even though it didn't say heat. If it's tertiary, it can't do
be.
anything else but E2 with a strong base. Is it a bulky base? Non-bulky base.
Non-bulky.
So Zaitsev's or Hoffman's?
Zaitsev's.
So where would the double bond be?
Inside in the ring.
Agreed? Everybody following this? Okay, last one. What do you think? SN1, SN2,
SN1.
E2, E1. Absolutely.
SN.
SN1. It's a weak base, weak nucleophile, SN1. And again, it's going to do carbocation mechanism which can rearrange. So what will the major product be?
OH in the tertiary allylic position.
And racemic mixture, because stereochemistry is shown, so we have to make sure that we show it. You can either draw out, totally okay to draw out both products, or just say racemic or something to indicate. Actually, in this case, oh wait, I've made a mistake here. Tell me if you catch my mistake. The mistake is in these two reactions. I've got a mistake there. Tell me if you can catch it.
1, 2, 3, 4. 1, 2, 3, 4.
You didn't replace the
Oh,
methyl.
wait.
Say that again?
You didn't replace the methyl.
Why should I replace the methyl? Oh, okay, I have
You
another
put-
mistake. I have two mistakes.
You forgot to put another methyl there.
I count your carbons, right? Count your fishing carbons.
Fishing. Getting close.
Closer and closer.
Yeah,
Oh,
your
then
car.
it's fine. Okay, then it's fine. I was thinking about, are they going to be enantiomers or diastereomers? But no, you're right. Now that there are two methyls, they have to be enantiomers. Count those darn carbons.
Yeah, count those carbons.
Okay, last one, guys, on the board, which is not on that handout. What if you were given the products and you had to select what to use? Again, the idea is, well, is it going to be SN2 or SN1 or E2? And then you decide based on that. So let's start with the substrate here. Is that primary, secondary, tertiary?
Tertiary.
If it's tertiary, which mechanism can it not do?
SN2.
So we are really only thinking about E2 and SN1. Isn't that right?
Yep.
So if you're going in this direction, from alkyl chloride to alcohol, is that SN1 or E2?
SN1.
So for SN1, do we need a strong nucleophile or a weak nucleophile?
Weak nucleophile.
What nucleophile would you use that's a weak nucleophile?
H2O.
Done. What if I chose hydroxide? That can actually favor E2. and not SN2, SN1. So if you want SN1, you got to choose a weak nucleophile, especially with a tertiary substrate. Make sense, everybody?
Yeah.
Okay, next one. What about this, guys? That primary, secondary, tertiary.
Primary.
Now,
Primary.
what are we doing? Are we doing substitution or are we doing elimination?
Substitution.
So, SN2 or SN1 for primary?
SN2.
So what do we need? Do we need a good nucleophile for primary, SN2,
Yes.
or a weak nucleophile? So what's a good nucleophile version of OH?
And
That's when you need
NaOH.
NaOH, KOH, whatever, exactly. You need the hydroxide. Do you see the difference?
Mm-hmm.
Okay, what about that tertiary substrate going here? Is that elimination or substitution?
Elimination.
So do we need a good base or a weak base? Good base. And then is it Zaitsev's or Hoffman's?
Hoffman's.
Hoffman's
So we need
product. A bulky base.
And honestly, the one that comes to mind is T-butoxide is kind of the bulky as it gets.
How did we
Yes.
figure out that it was bulky? I'm just trying to put it in perspective in my.
Did we go in the less substituted alkene direction or the more substituted alkene? Is that the Zaitsev's product or Hoffman product?
Okay.
Hoffman's product.
We good?
The
Good.
bottom. The
But then if
bottom.
you wanted Zaitsev's product,
Okay.
what would you change?
The small.
So what are
Oh.
the smalls?
Mhm.
You can ethyl or methyl, exactly, alkoxide. Of course, since it's elimination, there's no harm in adding heat to the mix because heat favors, makes the elimination go a little bit better. Make sense, everybody?
Mm-hmm.
So this is really this chapter is one of, as I've said before, is one of the most important chapters because it kind of creates that foundational knowledge of these four very important mechanisms: SN1, SN2, E1, E2. Of course, E1 is never the primary mechanism, but we should always know what it is. Can I answer any questions? You will see a lot of these things come up again and again and again as we go through other topics. You will see these things coming back in different forms, but
They'll be
if
there.
there are no questions, we can get started with the next chapter that's on the list, and that's chapter 7. Actually, we are going back to the order of the chapters 7. And chapter 7 is an introduction to alkenes. Chapter 8 is the details of alkenes. Oh, wait a second. I kind of try to draw out a perspective
February 3rd.
of what we've done so far. See if that makes sense. I hope I can. So we've seen that alcohols can be converted into alkyl halides, right?
Mm-hmm.
And we have also seen that alcohols can be converted into OTS, which can do a substitution in this direction. We have also seen that elimination. Actually, we will see later on. Later on we'll see how this can also happen. We've also seen the Hoffman product coming from there, and then these two with good leading groups can basically give us a bunch of different compounds depending on what our nucleophile is. We can do different kinds of substitutions. So another thing to add to this is, yes, we can go in opposite direction as well. Yes, we can go in opposite direction as well. Not that way we can't. This is E2 and E2. Of course, one is Hoffman, the other is Zaitsev's by the choice of the base, bulky base versus Oh, sorry, that's Zetsevs, sorry. Zetsevs, and this is Hoffman. And all of this is mostly SN2, but sometimes it can also be SN1 depending on what substrate you're using, and so on and so forth. So, I mean, that's kind of what we've learned in this chapter. Of course, don't look at it as one big thing, look at each piece. Yeah, we haven't done this part yet, maybe we'll do it later. But yeah, we can convert alcohols to alkyl halides, but alkyl halides can go back, SN1 or SN2, blah, blah, blah. We've talked about these. Guys, just please stop me, ask me if any part of this last chapter is not clear. Okay, then let's start talking about alkenes. That's chapter 7. What are alkenes, anybody?
Hydrocarbons with double bonds on them.
Hydrocarbons with carbon-carbon double bonds on them. Those are called alkenes. If there is one pi bond, how many hydrogen atoms are lost, so to speak? How many hydrogen atoms does one pi bond cost?
2 hydrogens.
So what will be the general chemical formula of an alkene if there are n carbons?
H2N.
Do you all agree? Because alkanes is CnH2n plus 2. Does that ring a bell?
Mm-hmm.
If every pi bond costs us 2 hydrogens, then alkene with 1 pi bond should be CnH2n. Everybody okay? What do you think are cycloalkenes? What? Say again? That's an example. So what are cycloalkenes? They're alkenes in a ring, right? So what do you think will be the general formula for a cycloalkene with 1 pi bond and 1 ring? Anybody? How many hydrogens does 1 pi bond cost us?
2 hydrogen.
How many hydrogens does 1 ring cost us? 2 as well. So what would be the general formula?
H2n minus 2.
Exactly. Our starting comparison is alkane, fully saturated. That's as saturated as it can be. So every ring costs us 2 hydrogens, every pi bond costs us 2 hydrogens as well. Does that make sense, everyone?
Mm-hmm.
This reminds me then the whole idea of IHDs. Do you all remember the calculations of IHDs?
Yes.
Mhm.
Does anybody have any questions in the how to figure out IHDs?
1/2 C saturated minus
Modified, depending
Modified
on
formula.
what's in there. Okay, so since we've already covered that extensively, I can skip that part in this chapter. Okay, cool. I often get this, guys. So if you think about an alkene with carbon-carbon double bond, what is the hybridization of this carbon
sp2.
and that carbon? sp2?
Mhm.
So what should be the shape at that place of the molecule?
Trigonal
So
planar.
both of those carbons should be trigonal what?
Planar.
Planar. Bond angles of
120 degrees.
about 120. Of course, there's going to be distortion because of the high electrons. They take more space. But it's around that. Agreed?
Mm-hmm.
So is it possible for an alkene to be, can an alkene be drawn like that?
Yes.
Can an alkene be drawn like this?
No.
No,
No.
let me finish.
Huh.
Let me finish. Can I draw an alkene like this?
Yes. Yes.
Yes,
Mm-hmm.
because this alkene is along the surface of the board. This alkene is perpendicular to the surface, right?
Mm-hmm.
Can I draw an alkene, which I get a lot and I always wonder why? How is this even possible?
No.
Is that possible?
No.
So please, when you're drawing your molecules, you got to pay attention to the geometry. You got to make sure you're drawing it in a certain way that actually is possible even. Is that possible?
No.
So the carbons of that double bond have to be planar because of their hybridizations. Last class I gave you the order of stability of alkenes, am I right?
Mm-hmm.
Cool. Okay, so we're done with that. Let's talk about naming alkenes. IUPAC nomenclature of alkenes. The word alkene can be divided into three parts. Just like the word alkane can be divided into three parts, the word alkene is really a combination of three parts. And the first part is alk. The second part is En, and the third is the E at the end. Can someone tell me, remind me, what does this tell us?
Number of carbons.
In what?
Number of carbons in the molecule.
No.
Oh,
What does the alk tell us, anybody? It is the number of carbons, but in what?
Like the father chain or the mother chain?
longest
In the parent.
parent chain.
Number of carbons in the parent. So what is the parent in an alkene? What's the parent in an alkane?
The longest string.
Right. So what's the parent in an alkene? It is the longest carbon chain, but
With a double bond.
which contains the double bond. Even if that means you have to select a smaller because that's the one that contains the double bond, then you must. But the parent must have the double bond included in that chain. Absolutely. What does the En tell us? This tells us that there is a carbon-carbon double bond in the parent. And what does the E at the end tell us?
The
Hydrocarbon.
it's a hydrocarbon.
No heteroatoms, no oxygens, no nitrogens, no nothing. It's a hydrocarbon. That's what the E at the end tells us. We good, everybody?
Mm-hmm.
So, for example, let's start with this. What's the parent? Your first step should always be finding the parent. What's the parent? 1, 2, 3, 4, 5, 6.
Yep, it is the
So
parent.
the alk is hex. Isn't that right?
Yep.
Now the ene. Where is the ene? So now we must give the position of the ene because it's possible to be in different places. We must give its position. How do we give the position? We number the parent chain. Isn't that right?
Yep.
The parent chain is numbered. Who gets the lower number this time?
1, 2, 3, carbon free.
It's the carbon-carbon double bond, that's our focus. That's the parent. So you must number the parent chain in such a way that the carbons of the double bond get the smallest possible numbers. Now in this case, of course, I chose it very symmetrically. Whether you count it from here or
1,
there,
2,
you'll get
3.
the same. Am I right?
Yep.
So, hex 3,
Hex free.
because you're giving the position of the ene,
Hex free eaten.
right? And then it's a hydrocarbon, there are no heteroatoms. Now, olden style, this is the more newer way of IUPAC numbering, and I love this method because it lets you do so much as we go through other families of compounds. You will see that. But older naming could have been just 3-hexene, and that's fine. I would encourage you to start using this methodology because as you start tagging on other families together and together, this method actually is way better, way easier than that method. Does that make sense, everybody?
Mhm.
I do see that I'm out of time, so I'm gonna stop here. Now, Wednesday, we will finish the nomenclature. I think we can actually finish this chapter because there isn't a whole lot in this chapter. It's really just an introduction of alkenes. So please come prepared with that, okay? We'll do more naming on Wednesday.
Tax-free. Okay.
You have a few seconds?
Yes, absolutely.
Good nucleophile, good base. SN2, E2. Good nucleophile, weak base, SN2. Good bulky base, E2.
I mean, that was.
Strong base,
Yes, but that's secondary. This is secondary. There's no added stuff. So
I
there's
get,
motivation.
okay, so
Yes.
that's
Yes.
issue number one.
Okay.
strong base is SN2. Weak nucleophile, weak base.
But very.
All right, so you don't want to hear.
Okay.
Fine. And then the other question.
Yes.
SN1.
Did you say regio isomers
Yes,
already?
I said region. I have a question. One from the original.
Right, I get one from the original,
Um,
and I get two from this one.
And then Miss Tanya. So what was the original?
So this is the original. And I get one from that.
So,
Next thing you know, it's like,
right?
And then,
And then
It's the end of the
yeah, right?
Go like this.
yes, okay.
So there's beta here.
And there's a
There's
beta
beta
there,
there.
right.
Wow.
So that's three.
we've only.
Yeah.
Is that four?
That's one.
Five.
One from the original and three from the. There's beta right here. There's beta right here.
Oh, Jiminy, there's a way over there. Okay, thank you.
Brain fart, I guess.
Yes. You got what you came expecting. That I did, that I got. So, is it increasing? Why did that? That's tertiary.
Well, here we go.
Yeah.
Don't want to risk it. So your experimental one, you can understand if they're not following the rule, right? Because then you can say there's an error somewhere. Where to expect it? Oh, I didn't draw.
Dash is not in biology, is he?
What?
Is Dash in biology?
No, Dash is not in bio.
Between essential or this tertiary should be the slowest.
Almost everyone in this class is in bio.
Yeah.
I think there are 4 students that are not in
Chlorine
bio.
is a better leading group than chlorine. So you would expect that to be faster. Protein will be very fast because it's resonance, and benzene will be very fast for both. Yeah. So, yeah, I would expect this to be there. I think this, I would expect it to be here. Yeah, this should be, okay, here's my expectation with it. Going increasing. 1, because it's sp2. 2, because it's tertiary. Now I'm looking for secondary. I'm seeing 1, 2, 3, 4. But that's CL. Those are PRs. But those are ring structures, although we didn't really talk about that part. So I would expect the CL to react slower than BRs, because BRs is a better leaving group, so they should react faster. And then come the primer. Without a doubt, I would expect them to be faster because of also resonance. And between them, yes, I would expect this to be faster than that. Yeah, so if you got that to be, I think I can understand that, just because that's such a good leaving group that maybe the secondary surpass the primary because the leaving group is so much better, I can understand. But this is your observed, this is not
This is
expected.
the
Yeah,
observed,
yeah, that's fine.
Okay, and then for error, like,
Yeah.
what do you, like, maybe
I
I
think
just
the
did.
only error I see here is that it's really not a very scientific way of doing comparisons, right?
Yeah,
I mean, when
yeah.
you're adding, how do you know you started exactly at the same time?
Yeah, you have to like
We really don't
add, but then go back. and look.
Exactly, exactly. So, technically, if you wanted to really do this experiment, such that T0 is the same for every substrate, then you have to devise a better,
Probably have to do them 10
Yeah.
separately or.
or something you
Yeah.
have to do where you can keep an accurate time
Yeah.
of everything. Yeah, that's kind of it.
Okay, thank you.
Yeah.
Yes.
Hey, yes, Em.
So since I'm not gonna be here tomorrow, could I turn in my notebook early?
Oh, she's
Sure, yeah.